So if you ever wanted to see if anybody's listening or paying attention, say something like nothing is future-proof with no context, and you'll get hit with all kinds of exceptions. Today I'm going to talk specifically about Automotive Ethernet, and that term future-proof is, you hear it a lot in the context of Ethernet networks, but it's not inherently future-proof. There's a lot of activity going on to keep it future-proof or keep it relevant. So I'm going to give an introduction, followed by the history of Ethernet evolution, what has happened from the beginning, back when things were 10 megabit coax, to today. Then I'll talk about what's happening in two different organizations, IEEE and Open Alliance. So typically, if there's any new work being done or specifying or standardizing something related to Ethernet or Automotive Ethernet, it's either in IEEE or Open Alliance. So what's meant by future-proof? Well, in this context, it's something that has a core design that's upgradable in terms of features, functions, bug fixes for the foreseeable life of the product. Some of the enabling technologies behind this have been microcontrollers, flash memory, standardized interfaces for peripherals, and then you don't always think about it, but the service and support infrastructure. You know, something like Android App Store, or in dealers, kind of a infrastructure there to pass on software upgrades. But I say, strictly speaking, nothing's future-proof for a number of reasons. One, the core design of any electronic box is the CPU, and it's got a finite amount of throughput. So in terms of new requirements or emerging features, that's going to be kind of the ceiling there. Similar with the bandwidth of CPU interfaces that connect to that CPU for connecting peripherals. Another thing is disrupting technology, something that just kind of is a game changer and makes certain things obsolete. And at some point, if you're adding on and adding on and adding on, you basically have more duct tape than you do with design, and it's just not worth trying to maintain something. That's not to say we shouldn't aspire to have future-proofness. So a strategy for incrementally approaching something that's future-proof is to embrace a technology that has a demonstrated history of extensibility or evolving to meet new requirements, commitment to backward compatibility, and then a strong and healthy ecosystem and talent pool to use this technology. So Ethernet's growth in automotive networks is directly related to these three attributes. When you go back at looking at the origins of Ethernet, looking at the physical layer, around 1983, we were looking at 10 megabits over coax. It was half duplex. It had collisions and managing collisions. So today, the latest spec was released in 2022, 802.3, defined all the different physical media of Ethernet. 80 plus revisions, 7,000 pages. The table of contents alone is 160 pages. So there's been a lot of work done in the last 30, 40 years. So now we have well over 100 gigabits per second. We have a switch duplex, switch network, so full duplex, no collision. We have power over Ethernet, power over data lines. We have flow control, and last but not least, or the most important to us, is Automotive Ethernet. So now we're looking at 100 to 10 gigabit standards existing, 25 plus gigabits in development, and then also some low-cost work in the area of 10 megabits. That's the physical layer. That's, now talking about the architecture, what's residing on the physical layer. 802.1 is a working group that works on the standards related to Ethernet architecture. So it was started around 1990. The initial work was defining what today we call a switch. In IEEE terms, that's a bridge. So that specification, 802.1Q, or let's say the most prominent specification in this group of specifications is 802.1Q, just released. So that's had 40 amendments, 2,000 pages, that only has a 60-page table of contents. And so this is encompasses, probably if you're working in Ethernet, a lot of terms you're familiar with. Spanning tree protocol, which isn't relevant to automotive, but it's a big part of this document. Quality of service, VLANs, prioritized queuing, which is a means to quality of service, traffic shaping, policing, and bandwidth reservation. And then there's another whole host of other 802.1 documents that are related to security, to time synchronization, audio-video bridging, time-sensitive networking, and some redundancy techniques for reliability. And you can see some of the dates here. The first date is when that standard was first started working on, and then the last date. So you can see MaxSec, they started talking about it in 2006, and they talked about it as recently as 2018. TimeSync, back in 2011, they're still talking about it in 2020, and they're still talking about it today. What can be done better? So without this ongoing development for the last at least 15 years, we wouldn't be talking about Ethernet vehicles. And we wouldn't be talking about it going forward if the things I'm going to explain to you today weren't happening. So the most active developments, if you had to bin them into different categories, would be higher speeds. We learned why higher speeds are needed earlier when Cole was talking about zonal architectures. You have more sensors, more data, more bandwidth, and all of that's being aggregated and sent back to the central device. So you need a big, fat backbone. Lower speeds, 10BC1S, single twisted pair Ethernet, that's been released. We have a workshop on it this afternoon if you're interested in how it works at the low level. But they weren't happy. Nobody was, you can't make everyone happy. And of course, they found plenty of things they can improve on. So we'll talk about the enhancements that are being worked on in the standard. Time-sensitive networking. So this is mechanisms for quality of service that are needed for these new features that have time-critical or safety-critical applications. 802.1BG, that is the automotive profile for time-sensitive networking. I'll explain what that is. They made some enhancements to a transport protocol used in time-sensitive network, and basically it's encapsulating legacy networks or sensor data into a common PDU. Also talk about what's going on with energy efficiency and network security. When they decide to pursue an amendment to 802.3, the IEEE has a whole process of identifying the technology, getting approval to work on it, and commencing that work. When you look at the amendments specifically for Automotive Ethernet, there's some common requirements that are in there. I'm not going to say these, what I'm going to talk about are in every amendment, but they're in almost all of them. So the first thing you'll see in the objectives of these work groups is to preserve the MAC interface. And that's very important because of the layered architecture. One of the big selling points of Automotive Ethernet was you can change the underlying media and everything else above it stays the same. If you start changing that interface or that MAC interface between the layer 2 and layer 1, all of that breaks. So this is very important. Obviously supporting automotive environment requirements, not forgetting about ENC requirements, STC and CISPR, and kind of setting a level for the bit error rate or the signal quality between two link partners to achieve minimize the number of frames dropped due to corruption. And then there's some optional things that are pretty common in these specs for auto negotiation. The two PHYs will advertise their capabilities in terms of speed or whether they're going to supply the clock or use the other PHY's clock. Energy efficient optimization for certain modes of operation of the PHY. Fast wake up, a requirement to be able to be up and sending a frame with sending and receiving valid data within 100 milliseconds, and then power over data lines. 802.3 CY. This is where, right now, we have a demo out there showing 2.5, 5, and 10 gigabit automotive Ethernet. This picks up where that left off. It's called greater than 10 gigabit electrical automotive Ethernet by task force. So they had a fairly broad scope when this was first kicked off. They were looking at 25, 50, and 100 gigabits per second over automotive cabling. And constraints on this were 2 inline connectors of up to 11 meters. So this was reduced from all the automotive Ethernet, 100 gigabit and multi-gig to this point, because those are 15 meters and 4 interconnects to achieve greater than 10 gigabits per second. They had to make some concessions on the requirements. They thought that this was, since this isn't going to be all over the vehicle, that was a fair compromise to reduce the length and reduce the number of interconnects. One of the things they determined in this group was we've really hit the limit of how much data we can push through two wires or a single twisted pair in the automotive. So 25 gigabits is the maximum transfer rate that anybody's willing to discuss going over a single twisted pair. And at some point last year, they decided that rather than drag down the progress or the release of 25 gigabits, they would strike the 50 and 100 gigabit requirements to this part to ensure that the schedule could be maintained. So it's not like they completely threw away 50 and 100 gigabits. There'll be continuation of this, and the groundwork set by 25 gigabit will be used to achieve 50 and 100 gigabit. So this greater than, so that basically the 25 gigabit per second, that standard is going to, is scheduled for sponsor ballot completion within the next few months. What that means is the group that sponsored it and wants to see this happen is okay with the specification, and they're going to hand it off to the powers that be that make it an IEEE standard. So how do we get to beyond 25 gigabits per second? So as I alluded to in the last slide, plans to adapt existing techniques that are currently used in optical interfaces. And so multiple 25 gig G-base-T1 PHYs will be aggregated in what's called the reconciliation layer. So that's the layer between the MAC interface and the MII or XMII. So these different PHYs, they can be used in full aggregation. So you can have a 100 gigabit MAC connected to 4 PHYs. They are logically, for all intents and purposes, it's one link. Or you could split that. If you have a system on chip with multiple MACs, you could have a 50 gigabit, 25 and 25, or 75 and 25. So there's a lot of flexibility in how you use these multiple PHYs. And if you're familiar with the term link aggregation, this is similar to that. In switches, there is a way to configure the switch to treat two network connections as one logical connection. This is very similar to that, but it's at a lower layer. So I don't know all the trade-offs, but I was told that there are a significant number of constraints with link aggregation relative to this PHY bonding. Any questions so far? Okay. Question always comes up about optical. Optical is always associated with faster speeds than copper, and there's a lot of truth to that. In automotive Ethernet, they're looking at two different types of optical. There's glass optical, index glass optical fiber, and so that's being worked in a task force 802.3CZ. So they're looking at 2.5, 5, 10, and 25 gigabits over 40 meters with 4 inline connections, and 50 gigabits over 40 meters and 2 inline connections. So the timeline of this, it was approved about a year ago, and they're looking at the standard to be approved late this year. There's also plastic optical fiber. There's advantages and disadvantages to the technologies in terms of cost, performance, reliability. 802.dh is for plastic optical fiber, and so it's going towards 2.5, 5, and 10 gigabits over 15 meters, 3 inline connections, and then only 25 gigabits, 15 meters, and 2 inline connections. And so that was kicked off about a year ago, and target date for that approval is the end of next year. There's always the question of why haven't we seen optical in automotive? Historically, the first arguments were not concerned with reliability in the environment and routing. The bend radius, go past the bend radius so much it degrades the signal, concerns with abrasion and physical abrasion in the vehicle, in the environment. There's been a lot of work to put those concerns to rest, but I think the biggest one that remains is it's not serviceable. You can't cut and splice. If you have a break in the harness, you can't splice it together. To be able to roll that ability out, across all the dealers and all the tools and all the training, and it's at this point it's cost prohibitive, and the result of a broken cable or broken fiber optic cable would be almost the total of the vehicle when you look at the cost of pulling out the entire harness to replace that. That's your question. Yes. Yeah. Mm-hmm. And that would be like my bigger concern. Yeah, I agree. The companies like Corning and the ones behind trying to pitch this for new sales, they go to great lengths to put those to rest. But I think the insurmountable one at this point is just the ability to service. Yes, and again, the materials companies are coming out with all kinds of enhancements for bend radius and temperature and jacketing for abrasion, and they're addressing all those concerns. But I think until the OEMs step up and think about, is this a good thing, and is it worth the investment to look at this? It's just I don't think it's going to get much traction. Enhancements to 10 megabit. One of the biggest things critical to 10-T1S was it only supported 8 nodes, or at least 8, or up to 8 nodes. So that in talking with the 5 manufacturers, there's nothing that prevents their PHYs today from supporting more than 8 nodes. It was just concern about standardizing something to support beyond that and having a good understanding of what the requirements needed to be. So again, rather than have delayed the release or approve of the standard, they decided to cut the scope a little bit and then circle back and work on this. So now they're working at 16 nodes up to 50 meter reach instead of what today we have 8 nodes and 25 meter reach. Single MDI connector, so specified connector on 100 megabit and gigabit. There were no standardized connectors, so you had TE, you had Molex, you had Rosenberger. We got to gigabit, or multi-gigabit. Now we're looking at standardizing that. They're also looking at standardizing 10 megabit. Dynamic configuration. These are some things to do with avoiding static configuration in the vehicle, assigning node ID dynamically, and then plug and play in the context of power over data lines or power delivery. And then other performance enhancements, and then those bullet maybe isn't, I should change it, performance enhancements and reinforcements that some of the same requirements are in effect. We're not going to put 16 nodes, 50 meters, and allow a lower bit error ratio, or some other requirement that was in the original requirements. 802.1dg, the standard is the automotive profile for time-sensitive networking. And what that is, you have half a dozen or a dozen standards of time synchronization, network architecture, switches, and this is trying to distill that down into a set of minimum and optimal requirements needed for automotive networks. So it points to a lot of these specs and says, this is important, this is not. It has some advice or an annex of best practices, how to make all these things work together, not against each other. It's currently a draft, and it was supposed to be completed this year, but they're asking for an extension into next year, or beyond this year. So it has a base profile, and it is comprised of time synchronization, stream filtering and policing, and then credit-based shaping, which is the means of traffic shaping. So that's the base profile. Then they have an advanced or extended profile, and that talks about time synchronization enhancements, multiple grandmasters, multiple time domains, redundancy, redundant frames going different paths in the vehicle. Traffic conditioning, they added, in addition to credit-based shaping, they added time-aware shaping and asynchronous traffic shaping. There are a couple standards that are typically talked about when you're talking about time-sensitive networking, specifically CQF, cyclical queuing and forwarding, and frame preemption. At least at this point, the author and really the work group doesn't see how to fit those in with all these other standards and mechanisms for quality of service and not have a big mess. Because TSN is kind of like a toolbox. You can pick and choose different things to achieve your network requirements. But if you throw everything in there, things aren't going to work well. Things will work against each other. So at least these two, they felt that they didn't see a way to insert them and give a good explanation of how to use them without throwing up, other things on the network. 1722, some minor changes here, the transport protocol for encapsulating networks. So it's improving some of the subtypes or header information for CAN and LIN. So the information carried in the header along with the frame, the data contents of the CAN frame. Some other enhancements, sequence numbers and being made larger, support for multiple clock domains and changing grandmasters under fault conditions. And it also puts some guidance in there on what to do if you receive PDUs or ABTP PDUs and out of order. Any questions so far? I'm running out of time, so I'm going to 5 minutes. Okay, here we go. The Open Alliance is a special interest group. If you're not familiar with them, their main focus is interoperability between devices and device suppliers. So they have a long list of technical committees for a bunch of different technologies, a bunch of different use cases. Where the most work today is being done, or the most discussion today, is TC10, which I've highlighted. That has to do with wake up and sleep on an automotive Ethernet network. Interoperability appliance test for 10BASE-T1S and MACsec. So sleep-wake, the TC10, this is something that's been established. It is the lowest level of power moding for sleep-wake up for an automotive Ethernet network. So it's at the PHY. It has a global topology. Because it's at the PHY, you don't need microcontroller interaction to manage this. And it has some requirements for maximum wake up time and It shouldn't be confused with energy efficient Ethernet. So this is a sleep-wake strategy. Energy efficient Ethernet has to do with the PHY switching into lower power consumption modes if idle traffic or asymmetric traffic where it's only really receiving a lot of traffic in one direction. It's at the PHY level. So the sleep wake up request comes from the PHY. So to monitor those or trigger those, you need to write directly to PHY registers with some application. And it's basically, as you might expect, a handshake between the two devices. So you write with one PHY, say, send a wake up request. The other PHY that sees it, sets the flag in a register and responds. And then if there's silence between the two, then they both go to sleep. And the way this is done is on the wire, there are symbols which are, I guess you could think of it as control information for the network that aren't part of the data. They're kind of multiplexed in there. And so these are symbols that you can't see in Wireshark. They're basically all you can see them. The way to see them is by reading and writing these registers. And then MaxSec, am I out of time here? So MaxSec, this is the lowest. We talk about the lowest layer level of power modem. MaxSec is the lowest level of security. So security at the MAC level. So it provides hop-to-hop protection, everything on top of it. So it can do anything from just authenticating it came from the proper source, verifying that nothing has changed in that information. You can also optionally encrypt the information. And then it has a counter in there for the guard against replay attacks, replay protection. And the way this is achieved is stuffing more information into the Ethernet frame. So now, in addition to the destination addresses, source and destination, ether type, and CRC, now you have an ether type saying this has MaxSec information in it. And then this is the MaxSec information. So you have this is the rolling counter, the packet number for replay mitigation. And this integrity check value is basically a hash that's run on the entire payload, ether type of VLAN. And that's what's used by the receiver with the key to determine if anything has changed in the source address and anything else in the payload. So I think I'm out of time, but I think I covered as much as I possibly could.